All right, folks, so as promised, and I know it's been a while, but we are going to do a tutorial video over chapter 8. So what you guys want to have in front of you at the moment is your chapter 8 review, chemical reactions, and we're going to walk through some samples of this and try not to take too much of your time. But hopefully those of you at home, a little stuck, feeling like you're not getting something or losing some details here and there, hopefully we can kind of iron those out in this video format. So we'll see, okay? I have a lot to remember, a lot to go through, so we'll see how long this takes, but bear with me, right? And if you get one, you want to skip ahead, do that, all right? So what we will be doing, we're going to do 2 sample problems from section 8.1, version number 3 and number 5 from that front page. Bam, bam. All right, then we are going to go to section 8.2, right? And we're going to focus on number 7, A and B. All right, then we'll go to section 8.3, which is kind of the crux of this chapter. And we will do number 2A together, and then likewise number 3 together, which is one of those net ionic equations. Like I said, this is going to be a little sampling of everything along the way. So again, make sure you've got this guy in front of you. Now, the tools we also need in place to do these successfully, unless you've got a terrific memory, you want to have this paper right here in front of you, right? It's got our list of polyatomic ions. It's got our solubility rules, and over here, our nifty activity series. And we need these to predict the form that products take, and also to predict whether a reaction actually occurs. All right, I'm going to walk you guys through step by step, nice and slow. Kind of start with skeleton reactions where we began a chapter and build our way up slowly. And maybe there was just a detail earlier on that you missed that's going to get fixed today. We'll see. Okay, so without further ado, I'm going to use a handy black marker and a handy blue marker. I might even throw a green in the red just to get crazy. Okay, so without further ado, like I said, number 3. We want to produce a skeleton equation. All right, now, the skeleton equation here, I'll underline that term. That means we don't need to balance it. We just need to write correct formulas. Now, could you balance a skeleton equation if you want? Sure, that's just not what I'm assessing when I ask for that. But if you go ahead and balance it, that's fine, okay? That just means you don't need to balance it, all right? And in this case, we want to show a skeleton equation for the decomposition of magnesium carbonate to produce magnesium oxide and carbon dioxide. Okay? So all we're going to do is we're going to write that word equation into the molecular equation form. Okay? And we're not going to have to worry about balancing it. All right? So what I have to do then is I have to take the names of my formulas and write the correct formula for it. So magnesium, as we know from the periodic table, is a +2 when it's an ion, part of an ionic compound. All right, carbonate, the ATE, tells you to go to your list of polyatomic ions. We're going to find that CO3, and we find that it is a -2. So my formula, because they're both 2s, is just going to be MgCO3. All right, so that is magnesium carbonate. Now I am going to decompose that, which means I'm taking one particular material, right? And oftentimes that means we heat it, and I think in the word problem on your paper it actually says heat, not decomposition, but that's what we're doing. All right, and so when we decompose something, we are taking the materials in this formula and we're going to split some of them up. Okay, and so in this one it says we produce magnesium oxide. So we already know magnesium is +2. Oxide is oxygen ions. And if you go to your periodic table, you find oxygen, we find that it's a -2. So my formula on this side is just going to be MgO, right? And it says and carbon dioxide, right? And so that di prefix meaning 2. So this is not an ionic compound, it is a covalent compound, which is why we throw that prefix in there, because covalent compounds aren't as predictable in terms of how many of each we get. So carbon just means we have one carbon. dioxide needs 2 oxygens. All right, there is our skeleton equation. Again, I take the charges I know, right, and I use that to produce my formula. They're both 2's, so it's just 1 of each, right? Plus 2 minus 2 makes 0, right? So 1 of each there. Magnesium oxide, plus 2 minus 2, so 1 of each. And then carbon dioxide, I don't use charges when it's 2 nonmetals. I use the name to tell you my formula. And the di tells me 2 oxygens. And there is my skeleton equation. Now, are we actually balanced in that case? Yeah, we already are. Just, you know, for purpose here, I got 1, 2, 3 oxygens, 3 oxygens. 1 carbon, magnesium, 1 magnesium. That's already balanced. But when it says skeleton equation, do we have to worry about balancing? No. But if you do, good. Good for you. Woo. All right. So, number 5. All right, gotta loosen up for this one. All right, it says, write balanced equation for the word equation, right? So we're doing the same thing for 5 and 6, but we're just gonna do number 5 together. And the word equation is aqueous silver nitrate plus copper metal yields silver metal plus aqueous copper nitrate. All right, so what we're gonna do here is very similar over here. We're gonna start with the skeleton equation, right? But this time it says balanced, right? So we have to, in this case, go back and balance if needed, right? It could be balanced when we write. We'll see. So we'll start with our skeleton equation and write with the correct formulas first, all right? So silver nitrate. Now silver is a transition metal, but you should know by now, silver is one of the transition metals that always has the same charge, and that's a +1. Nitrate, ATE, tells you to go to your polyatomic ions, right? You look there, you find nitrate is a -1, right? And copper metal, in this case, doesn't have a charge. It's just a metal by itself, all right? So let's write this side of the equation first. Silver nitrate, okay? So in this case, the formula for silver is Ag. The formula for nitrate is NO3. Now, it does tell me that that is aqueous, so I need to include that information right there. All right, and then I'm going to add copper metal to that. So copper metal, right, is a solid. Okay, now I'm going to produce a reaction there. All right, now in this case, I am telling you that copper does the reaction. In section 8.1, it's not so important, but whenever we have a single replacement reaction like this, just for the purpose of clarification, we would need to make sure that copper is indeed above silver on that activity series. Again, a lone metal needs to be above the metal ion for a reaction to occur. And of course, if you look at that activity series, right, we should be able to find copper down here toward the bottom, and it is above silver, so we're good, right? But, all right. Now, so we're producing silver metal. So silver metal is just going to be Ag, and that's going to be a solid, right? The metals are all solids except for mercury, which is a liquid, kind of a cool little thing, right? And then it says copper nitrate. Now, I am noticing that I did not tell you the charge of copper. My fault. You guys are used to me making stupid mistakes like that. But let's just say this is a +2, all right? Nitrate's a -1. We'll just call that a +2 this time. Now copper can vary because it is a transition metal. It could be a 3 sometimes, could be a 1 sometimes. We'll say this is copper 2 nitrate, all right? So I will not make that mistake on your test. Okay, I'll be sure to put that. Same thing with acids, by the way. I'm gonna put their formulas there for you, at least in parentheses, so we don't have to worry about getting those screwed up, okay? But in this case, we've got copper nitrate. Copper is a +2, right? Nitrate's a 1, so it's going to be 1 copper and 2 nitrates. And because nitrate is a polyatomic ion, that 3, remember, is just part of nitrate and we don't worry about it. But that 2 is important to us. We're going to have to put a 2 there. Okay? So now that we have our skeleton equation, we need to see if there's some balancing that has to occur. All right? So what we got to look at here is each element on both sides, right? Each individual element or polyatomic ion on both sides to be sure that we have the same amounts of everything. And that's what balance means, okay? So here, this shows 1 silver, right? So I'm gonna trace that to the right side, also 1 silver. So silver's good on both sides. Nitrate, I've got 1 of those. Again, that 3 is part of the nitrate molecule, okay? So that 3, we don't need to worry about it unless those oxygens somehow get split off in a decomposition reaction, right? So this tells me I have 1 nitrate. I'm gonna look over here. Oh, this little 2 outside the parentheses does matter, right? And that tells me I have 2 nitrates, okay? So I have a fundamental problem, conservation of matter right here, right? I can't just get an extra nitrate. I can't do that. You can't do that. Nobody can do that, right? So we need to show on the left side where that extra nitrate came from, all right? And the way we do that is with what we call a coefficient. Now, I can't just go over here and do that. No. Because that would make the wrong formula for silver nitrate, okay? So when we need to balance, we add coefficients, which means I'm gonna take my 2, to balance that on this side, I have to put it here, up in front of that silver. Okay, so now that gave me 2 silvers and 2 nitrates. So I took care of my 2 nitrates, but then by putting the 2 here, that gives me 2 silvers and just 1 there. Just like I can't create nitrates, I can't just get rid of silver. That doesn't happen either. All right, so I have to have 2 silvers here and 2 there. Right? So I'm going to add a coefficient there to try to make everything even. Now, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. Can we do this? We got 1 copper, 1 copper, gold. Okay? So that's kind of that section 8.1 stuff, learning to write our formulas correctly and then learning to go back and balance after we've written the correct formulas, right? We don't use subscripts to balance. And just because we got a subscript here doesn't mean it needs to be here. Just because we have one here doesn't mean we put it there. But in terms of the overall amount on both sides, right? If we end up with different subscripts for the same thing, we have to use coefficients to fix it so that we have the same total amount of atoms on both sides. All right? And we'll do some more of that when we get on to section 8.2 and 8.3. Okay? So I'm going to quickly slide this guy over. And this guy here. All right. So now we are moving on to section 8.2, and we're going to do 7A and B together from that section, right? So that would put you at page 2 of this, and then toward the bottom. All right? In which case, we're just going to complete reactions, balance them, all right? Now the added layer of complexity here is we now need to start determining whether a reaction actually occurs. So when I talked about that activity series earlier, back with number 5 from section 8.1, number 5 from section 8.1, that's what I was talking about, but here we're gonna actually have you predict, does the reaction occur or does it not, okay? And if it's a double replacement reaction, we would need to use solubility rules to determine does a reaction occur or does it not, all right? And I think I've got a couple examples of where they don't, so we can explain why, all right? So we'll start with 7A. It says bromine, liquid, reacts with sodium chloride solution. So the AQ means we've taken our sodium chloride and dissolved it into water. Looks like the salt disappears. As we all know, it doesn't disappear. It just separates into its ions of sodium and chlorine, right? And so what we need to decide though before, so what type of reaction is this? Single replacement. And how do we decide whether a single replacement reaction occurs? We use our activity series, right? When the elements are available, okay? So in this case, I've got bromine. Right? Now, bromine is not a metal, right? So most of the time we use this side of our activity series, okay? Now, we do have a slide over here that gives me a list of nonmetals. In this case, they're all halogens. That's that group 17 on the periodic table, right? But we use it in the same way. So, right, so what we have to decide is, will bromine replace the other nonmetals? So we're not going to compare bromine to sodium, right? Sodium's a metal, and a nonmetal won't replace some metal in this case, right? So bromine is one of the few liquids, right, as an element. But what it can replace is our chlorine, which is also a non-metal, right? And they also tend to actually are the same column, right? So they're going to do like things in chemical reactions within that same group, right? So what we need to compare is bromine to chlorine, all right? So if you go to that, right, we would see that chlorine, right there, Cl2 is above bromine. What does that mean? Okay, what that means is chlorine is more likely to be an ion than bromine is. And because of that, that means bromine will not be able to replace chlorine. So again, the way to read your activity series, the lone element needs to be above the element that it's replacing for a reaction to occur. In fact, bromine is not above chlorine. So therefore, we predict no reaction. Bam. All right. Now, if we go to the next one, we have calcium. Calcium is our lone element. In this case, it's a metal. So we're going to use this side of the table to first decide whether a reaction occurs or doesn't. All right. So for a reaction to occur, we need to find calcium on our activity series and look to see if it's above. Which one of these does it need to be above? In this case, calcium's a metal. So we find the other metal, which would be magnesium, all right? So go to your activity series, you find calcium. Ooh, it's way up there toward the top. Whoops, that's upside down for you guys. But no, it's not. So I'm reading this backwards. So we find calcium right there, right? And then we find magnesium, which is below calcium. So in this case, calcium is above magnesium. So there is a reaction, in which case we need to carry on, write our products on this side, and then go back and balance it. And we also need to predict, since we are given the fact that this is aqueous and this is solid, we should also include that notation on this side. All right? So this touches on our solubility rules. So we're going to produce, okay, in this case, calcium is going to replace magnesium. So calcium will combine with nitrate, and magnesium will be the lone metal on this side. All right? So the trick I kind of showed you guys for determining your formulas on the other side, again, is based on charges, right? So calcium, when it becomes an ion, will be a +2. And so I don't want you guys confused. Calcium metal doesn't have a +2 charge yet, okay? But when it ionizes, it will have a +2 charge, all right? In this case, magnesium, also +2, and again, we know that from the periodic table. Nitrate, from our polyatomic ion list, is a -1, all right? So, plus is gonna combine with a minus. So I'm gonna form calcium nitrate on this side, right? Which will be CaNO3, 2. And again, because calcium's a +2 and nitrate's a -1, that means I need 2 nitrates to neutralize it, okay? And that is going to be aqueous. Now, I know that's going to be aqueous because of my solubility rules. All right, so right here, I've got nitrates, right? Nitrates are always soluble, right? Which means they're always going to be aqueous, and there are no exceptions to that. So that tells me calcium nitrate will be aqueous when water is present, okay? And my other product forming here is going to be magnesium. But that magnesium is going to be a solid metal. All right? Whew, getting long-winded here. It's almost 20 minutes in. I'm sorry, but I just want to try to clarify as best I can for you guys. All right? So we're going to move on now to section 8.3, which is, again, kind of the crux of everything. We're going to do number 2A together because that gives us a little more practice with our solubility rules. All right? And how we predict double replacement reactions, right? How do we know if a double replacement reaction occurs? We have to use solubility rules, all right? And the general rule is with double replacement reactions, we usually start with two aqueous solutions, okay? If the products both end up soluble or aqueous, so both of them, that means no reaction occurs, all right? So it's not quite as easy to tell because we have to know what our products are going to be, right? And then look at the solubility rules to determine whether a reaction actually occurs. Unlike single replacement where we can look before we even carry out the reaction, all right? So here's what we're going to do. Again, so now these are aqueous. So when I write the charges up here, these actually are the charges because they're already ions, right? So zinc is a +2. Another transition metal that doesn't ever change its charge, always +2. Start to commit zinc, silver, stuff like that to memory, okay? Nitrate, -1. Tin. Now, tin is one of those far down elements on the right. It looks like it's in the non-metal section or like a +4 section. Tin is like a transition metal, okay? And so in this case, I can tell tin's charge because of this 2 here, because I know chlorine's a -1, right? Because it's in that -1 column. I don't always know tin's charge. It's often a 4, sometimes a 2, whatever, right? But this time I know tin, in this case, is a +2 because of that 2 there, okay? So now, my products, if I have a reaction, are going to be swapping my positive ions, or you can think of it as swapping your negative ions. It just depends on how you want to do that. It's the same thing, okay? So that tells me that zinc is going to be combined with chlorine, and that tin will combine with nitrate, all right? So I'm going to go ahead and write my formula, ZnCl2, and tin nitrate, SnNO3, 2. Okay? Now, before I bother with trying to balance this and checking whether it's balanced, I'm going to first decide whether zinc chloride is aqueous or solid, and then likewise with tin nitrate. Okay? So I'll start with zinc chloride because that's here first. So I need to find a rule that tells me something about either zinc or chlorine. And you guys, as you practice this more, you'll start to realize, oh, I want to look for chlorine, okay? So here's my 2 tables down here, my solubility rules. Now I'm going to look for something that's informative about zinc chloride. And when I get to this one right here, oh, I see a chlorine. Chlorine's a halide, right? Now, halides are usually aqueous, okay? Not always, but usually, okay? And the reason we say usually is there are exceptions. So if there's nothing written for exceptions, that means they're always aqueous, okay? Here, there are exceptions, so we say they're usually aqueous. Now, so we need to look to see whether zinc is an exception, okay? And if we look at that list, we see that our exceptions are silver, lead, and mercury. Zinc is not one of those, so that remains aqueous. Okay? Now over here I've got tin nitrate, and we already talked earlier about our nitrates, right? Nitrates are soluble, no exceptions. Also AQ. All right? So what happened in this, right? We have zinc chloride aqueous, tin nitrate aqueous. We are aqueous across the board here. All right? So what that tells me is, you know what? Don't even bother balancing that or worrying about balancing, because indeed we have no reaction. Okay? So that's what happened in that case. No reaction. We know that because both of our products are aqueous. Now, I do want to say this, even though my example doesn't have it. We got to be careful about these 2 tables. They tell us kind of opposite things. Well, not opposite. You have to read them differently. Let's be careful. So, on table 1 here, ions that form soluble compounds. That means these will usually be aqueous. These are when they're not aqueous. Okay? Over here, second table, excuse me, rise says ions that are that form insoluble. So what we have to realize is these are usually aqueous. The second table lists things that are usually solid. All right? Now, these all have exceptions. So here, aqueous, unless they're with these, which makes them solid. Here, solid, unless they're with one of those to make them aqueous. okay? So make sure we're reading the two different tables differently. Usually aqueous, usually solid, okay? All right, now, getting to this last one, we want to write a net ionic equation for reaction between barium nitrate and sodium sulfate. So what we have to decide, okay, is what's our molecular equation? Does the reaction actually occur? Meaning, do some of these aqueous solutions actually form a solid, precipitate, okay? Then we need to go and separate the aqueous solutions into ions, right? Cross out the ions that don't change from side to side. So in some of these double replacement reactions, we have what are called spectator ions that don't actually do anything. They just kind of hang out there in solution, all right? So we're identifying which ions actually are involved in the reaction. And they're the ones that go from aqueous to solid or something like that, okay? So 25 minutes in, man, I'm getting long-winded. Sorry about that. Okay, so barium nitrate, barium plus 2, nitrate minus 1. I get that from the periodic table and the polyatomic ion chart. Sodium sulfate, sodium's plus 1, sulfate minus 2. All right, so we're at barium nitrate. So barium, 1 barium, 2 nitrates, and that's aqueous. Plus, all right, we are now going to go to sodium sulfate, which is Na2SO4, aqueous. And that will yield if a reaction does occur, right? This is my plus 2, minus 1, plus 1, minus 2, right? My positive ions are going to swap places. That's going to produce sodium nitrate, which is aqueous, because nitrates are always aqueous, and barium sulfate, which is BaSO4. Now, we haven't looked at sulfates yet, so let's look at where sulfate is located. So we're going to look for some information about barium or sulfate, and I see we got some stuff about sulfates right here, right? So sulfates is in our usually aqueous column, all right? But we need to see, so sulfate in this case is with barium. So is barium an exception? So we're going to go to over here. Exceptions are calcium, strontium, barium, and lead. So barium is an exception. So when sulfate, which is usually aqueous, is with one of its exceptions, that makes it solid. Now, because we have aqueous, 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 solid, there is a reaction. We formed a precipitate in that reaction, okay? So now we're going to carry on and balance things. So I have 1 barium, that's good. 2 nitrates, 1 nitrate. So I am then going to put a coefficient of 2 right there, all right? Which also gives me 2 sodiums. Oh, hey, look at that, there's 2 sodiums there. Boom, that's nice. 1 sulfate, 1 sulfate. So by putting that 1 coefficient there, that does balance us out, okay? So now, that is my molecular equation. I'm going to write an ME right here, just to clarify. All right? So what I need to do then is anything that's aqueous, right? I'm going to separate those out into their ions. This is a lot of writing, and I'm going to try to hurry up here now. Okay? So what I have here is barium, 2 plus 2, NO3 minus. All right? Now, what I did there in that case was I took the 2. So when we write our net ionic equation or ionic equations, what we're doing is our added subscripts become coefficients, right? So notice that I still don't mess with that 3. We don't mess with our polyatomic ion subscripts. The only ones we worry about are the ones we add to it, okay? Now, so there's my ions, barium and nitrate, right? Now, my other ions are going to be 2 sodiums. Okay, again, that 2 becomes a coefficient because it's an added subscript, plus SO4 2 minus. Okay? So these are all my ions in solution when I mix them. Now some of these are going to combine with something else, some are going to stay ions. Right? So we'll finish that reaction out. Right here, 2 sodiums. Now this is aqueous, so that's a plus. plus 2 NO3 minus plus. Now, barium sulfate here is solid, right? Which means it is not separated into ions. That only happens when they are aqueous. So I'm going to leave this like this, BaSO4 solid. All right, now I'm running out of space here, so I'm going to adjust my camera a wee bit. All right, now what I have to do here is cross out my spectator ions. So these are the ions that don't actually change. So barium is a 2 plus here. It's not a 2 plus there, so that doesn't change. Nitrate is a 2 NO3 minus, 2 NO3. It does not change. Bam, and cross that out and that out. All right, now 2 Na plus looks the same on both sides. You cross it out, cross it out. SO4 2 minus becomes part of barium sulfate, so we do not cross that out. So what are we left with? So this is my total ionic equation. My net ionic equation is going to be Ba 2 plus plus SO4 2 minus yields BaSO4 solid. And that's it, all right? And that's gonna be kind of the crux. Like I said, I use that word crux a lot. It's a little climbing term of what we do in this chapter though, right? It's taking a word equation, writing the correct molecular equation, deciding whether a reaction occurs or not based on either activity series or solubility rules, right? If it does, we go back and balance it. Once we have a balanced molecular equation, we identify which are aqueous, right? And we write the ions for those aqueous solutions, right? Then we do that to both sides. And then we go back and we look, okay, some of these ions are the same on both sides. And if that's the case, that means they're not even part of that reaction. So let's get rid of them, all right? And then we rewrite our equation to show only the ions that are participating in the reaction. That's our net ionic equation. All right, this is a half an hour tutorial video. I'm sorry, but hopefully you guys find this helpful.